welcome back. We have been talking about chemical reactors for past several classes now, and today also we are going to continue the same trend. So, the topic is the same as before. We continue with talking about design of chemical reactors, and of late we have been working on several sets of problems, and we are trying to elucidate the concepts that we have learned as far as the design principles are concerned. We talked about CSTR, we talked about PFR, we also talked about batch reactors and certain polymerization reactions we also incorporated into the problem. Now, let us for a while stop doing the problems and let us come to the the main concept of this linking of polymerization with these chemical reactors. Until now, the basic principles that we have discussed, we never mentioned polymerization, although we have of late done some problems where we have discussed certain polymerization reactions with respect to chemical reactors. So, from now on, of course, when we continue to discuss the principles of chemical reactors, those principles will also apply to polymers as well as to your small molecules. I mean, we will also specifically start talking about polymers from now on, and then towards the next class, probably towards the end of the next class, or we will see how the things go. We will also do some problem where we will directly correlate the design principles with probably the complexity of different chemical reactions or also the polymerizations. So, speaking of polymerization, we have discussed the principle of radical polymerization as well as, if you remember, the step polymerization. So, the question naturally arises, let us say we have to do a radical polymerization, so chain growth polymerization. So, whether we will do the reaction in a batch reactor or whether we will do the reaction in a continuous start tank reactor, this is the question. Now, remember that when you are doing a reaction in a batch reactor, everything is put in together and then you wait for a certain amount of time and then you stop the reaction and you take it out. So, what is happening is that with time the concentration of different species is changing, you just allow the reaction to run its course. So, the conversion also is changing with time. If you remember, we did some problems where we related the conversion with time. If you are looking for a specific conversion, what is the time required, so on and so forth. So, this is something that you have to keep in mind in discussing this particular topic. If you are looking at CSTR, for example, what is happening is that you are fixing a specific conversion and then you are allowing this reactor to run at that particular condition. It is a steady state condition we are talking about, it is a steady state condition. So, the concentration of all the species, whether reactant or product, they do not change with time, and you are always getting a particular conversion when it is in running condition, the CSTR in that steady state. So, if you now discuss this difference with respect to whether we will do a free radical polymerization in a CSTR or a batch reactor, what will be your conclusion? Remember from our previous discussion on radical polymerizations that the radicals are normally very short lived unless you are doing a living radical chain polymerization. So, few seconds or less than a second. So, what will happen is that the chains that are growing, they will be dead in matter of seconds when you are talking about radical chain polymerization. Then another chain is growing, then another chain is growing, and that is the reason why the molecular weight is quite, you will get very high molecular weight species even at low percent conversion for radical polymerization, because high molecular weight species is formed quite quickly unlike in step polymers. So, the thing is then the propagating species or the chains that are growing, the lifetime of these chains is actually much lesser than the residence time of the batch reactor. If you are doing this reaction say in a batch reactor, say you are keeping for 1 hour the reaction, but each chain is growing within a matter of seconds and then they are dead. So, what is happening is that as the reaction is progressing, as you are allowing more and more time to progress, what is happening? Your concentration is changing. So, the chains that are growing at a later time point, they are seeing a different concentration of reactant, and the rate is a function of concentration. So, the rate also changes. So, what will happen is that all the chains that have grown at the end of the reaction, when you see different chains that you have, certain chains have grown at certain different time points and then they are dead. Once they are dead, they are not reacting any further. So, ultimately what is happening is that in the chain growth process, the radical chain growth process, what is happening is whatever chains you have, ultimately the dead polymers, they have experienced different conditions in this reactor, because simply they have formed at different time points and the concentration has also changed at those time points. So, ultimately the molecular weight distribution that you are going to get is going to be quite wide if you are doing the reaction in a batch reactor. Instead, if you did the same reaction in a CSTR, what would happen? If you did the same reaction in CSTR, it is a steady state condition. So, whether you are looking at time 10 seconds or you are looking at time 1 hour, your concentration is always the same. So, whatever chains are growing, whether the chains are growing at this time point or whether the chains are growing at that time point, at a separate time point, all of them are basically seeing the same condition, that is the same concentration. So, that is why the molecular distribution will be much narrower if you are doing the same free radical polymerization in CSTR rather than in batch reactor. So, if you are, so let us elaborate on this particular theme. Something that I have not discussed before, but I will assume here. If you remember that the polydispersity index, we did not derive in a statistical approach the polydispersity index expression for radical polymerization. We did the thing for step polymerization where this came as 1 plus p, if you remember. So, if the conversion is 1, then your PDI is 2, and we told that even though we want a narrow distribution, but for a step polymer we cannot get less than 2, because the p has to be close to 1, fractional conversion or fractional extent of reaction, it has to be close to 1. So, ultimately your step polymer of any reasonable molecular weight, that is industrially important, will have a PDI at least 2. This we actually discussed elaborately, but what we did not discuss is the expression of PDI for radical polymerization. Here I am going to assume this, just assume this, that if you have, I mean the expressions I am going to assume, I am not going to derive this. So, you can have two limits of PDI. PDI will be 2, I mean the attainable PDI will be 2 if the termination is happening through disproportionation. And this will be 1.5 if the termination is happening through coupling. Now, these limits that we have that can be derived, these are derived by considering that the monomer and polymer concentration are the same. Same means they do not change with time and they do not change with the course of the reaction. So, whatever monomer concentration is there, it remains the same throughout the reaction. Whatever polymer concentration is there, it remains the same throughout the reaction. By considering these aspects, it can be derived that the PDI is 2 for disproportionation termination and PDI is 1.5 for termination through only coupling. But this kind of situation cannot be realized in a batch reactor, because the monomer concentration and polymer concentration are not the same as a function of time, they are changing. So, these are unattainable limits for batch reactor. You will get in practice much higher PDI in a batch reactor if you are doing a radical polymerization. So, this is the limit for radical polymerization. However, these limits are attainable, quite attainable if you are doing the reaction in a CSTR, because in a CSTR that is being operated at a steady state, the monomer concentration and polymer concentration are not changing with time. So, there these things are attainable. So, either your PDI will be higher than this or it will be this, the lower value, the lowest value that you will have. So, these values can be attained if you can control your concentrations carefully in CSTR, but this is something that cannot be attained. This only tell you the ideal limit for a batch reactor, because for a batch reactor these concentrations are changing. So, ultimately the molecular weight distribution that you will get, the distribution will be broad, much broader when you are doing the reaction in a batch reactor, and here we are talking about free radical chain polymerization. And this limit of 2 and 1.5, they are attainable in a CSTR, because your monomer and polymer concentration do not change with time, it is a steady state condition. What happens with a step growth polymer? For a step growth polymer, you know that the chains whatever chains that are forming, here also I am just telling chain, polymer chain, those chains they keep on forming. There is nothing like termination. If you have say 10 mer, this 10 mer does not stay as 10 mer till the end. It can actually react with a monomer and form a 11 mer, or a 10 mer can react with another 10 mer. This kind of reaction keeps going on. And remember, this PDI value is 1 plus P, that is something that we derived for step polymerization before the statistical approach. So, this value 1 plus P, this means that your conversion has to be the if you go to higher and higher conversion, of course that is what you want for step polymers, because the molecular weight has to be higher. So, in a batch reactor what you can do, you just continue the reaction until close to 100%, then P is close to 1 and your PDI is close to 2. Okay. And also all the chains are basically growing as long as the reaction is progressing. So, the residence time is very close to being equal to the lifetime of all the chains for step polymers. So, all the chains basically they are experiencing the same change in concentration, because for the batch reactor as the reaction progresses the concentration is changing, all the chains are experiencing the same similar conditions, same change in concentration. So, that does not lead to broadening of molecular weight distribution for step polymers when the reaction is being done in a batch reactor. So, it is very simple then, you just do the reaction in a batch reactor, you allow the reaction to progress until close to 100% conversion, and then you have a your PDI value should be close to 2 because of the theoretical limit, and you have a reasonably narrow molecular distribution as is allowed from the statistical approach. It cannot be less than 2, but it can be very close to 2. Your problem is solved and you get a very high molecular weight. What happens? So, for step polymers then you can do the reaction in a batch reactor. However, for a free radical polymerization we better do in CSTR. What if we do the step polymerization in a CSTR? So, if you do the step polymerization in a CSTR, basically what will happen is that this xn, if you remember the Carothers equation, xn bar is equals to 1 divided by 1 minus p, and something that we are not going to derive, but we are going to assume this xw bar, that is the weight average degree of polymerization. If you are doing the step polymerization in a CSTR, continuously start tank reactor, then the expression of xw bar will be equal to 1 plus p square divided by 1 minus p whole square. We are not going to derive this, we are just going to assume this particular expression. So, the PDI, you remember PDI was 1 plus p in a batch reactor. Actually whatever we derived before was like your normal reaction that is going on in a batch reactor, it can be going on, you are going to 99% conversion, 100% conversion, and then this will be the expression. But for a CSTR, the expression of PDI then will be xw bar by xn bar, which will be equal to 1 plus p square divided by 1 minus p. So, in a CSTR if you are looking for a very high conversion, what is happening? If you go to higher and higher conversion, your PDI goes up, it goes towards very high value. So, in a CSTR what will happen is that your molecular weight distribution will be much wider if you are targeting very high conversion as compared to your batch reactor when you are talking about a step polymerization. So, that is the reason why we will not do typically the step polymerization reactions in a CSTR, because the PDI will go up without bound if you look at this particular expression. So, this is some general discussion that I wanted to do as far as in which kind of reactors you will do the reaction, if you have a radical polymerization, free radical polymerization, or if you have a step growth polymerization. Now, something else we are going to talk about. We are going to talk about steady state in little bit more detail. Remember these mole balances that we had derived, we talked about steady state equations, steady state for batch reactors, steady state for CSTR, so on and so forth. Now, we are going to look at the steady state, these steady states in little bit more detail, especially for CSTR, because it turns out that for CSTR there can be multiple steady states that are possible. We will come into more detail of this a little while after. Before that, we are going to talk about what we call as energy balance. You know, for mole balance, you know, you have to balance the masses. So, what is energy balance? When we are talking about, say, a steady state situation, let us say you are doing a reaction which is exothermic, it liberates heat. Say many of these vinyl polymerization reactions, say ethylene polymerization, it will liberate heat, exothermic reactions. If you are doing the reaction in a CSTR, it liberates some heat, so the reaction temperature might go up, but in steady state it is not allowed, because in steady state as a function of time all these properties have to be constant, so the temperature should not go away. So, we are talking about, say, an isothermal situation here. So, as the heat is released by the reaction mixture, that heat has to be taken away. So, you could put some coolant, a jacket around the CSTR that will take away the heat. So, in steady state then your rate of heat generation has to be equal to the rate of heat that is taken away. So, let us first try to understand this situation in a little bit more detailed way. So, we will call this as CSTR dynamics. Let us say we are doing an irreversible first order reaction, an exothermic reaction, in a continuously stirred tank reactor. Now, let us plot the reactor temperature on the x axis and rate of energy taken away. Okay. So, let us say this is RT. So, basically you have a CSTR, you are doing the reaction here and you may have a jacket around it where you have a coolant liquid. So, this liquid is going in and then it is also going out, and it is at a particular temperature, say CTC, and so this is, say, rate of energy or rate of heat removed, you can say also. So, rate of energy removed. Now, depending on the temperature, so this temperature T is basically the temperature inside the reactor. The rate of energy that is removed is basically a linear function of the temperature of the reactor. So, higher the temperature of the reactor, the rate of energy removed will be higher in a linear way. So, we will get something like this. So, rate of energy removed, so R for the removal, so RT, and this is as a function of temperature, this will vary like this. Now, this particular curve that I have drawn, this is for a specific condition. Specific condition means it could be for a specific temperature at the inlet, because you know the reaction mixture or the starting material that is entering, it will be at a certain temperature, let us say that is T0, that you can change, that you can increase or decrease. The same way you can also increase or decrease this temperature. So, let us say we talk about this T0. So, for different T0 values you will get different lines like this. Okay. We will come to that after. So, let us say then rate of energy removed by the coolant is basically equal to the, so it is basically linearly varying with respect to temperature. Now, if you are doing a reaction which is exothermic, irreversible reaction, it is also releasing some energy into the system, into the reaction mixture. How does that vary? So, I mean, let us label it like this: rate of energy release I mean this is the rate of energy released by the reacting mixture, because the reaction is going on. So, the temperature will rise if you do not take away the heat. So, this will be something like this. So, let us say that curve is GT, this is G for, let us say, energy release or energy, this is rate of generation. So, that is why it is G, okay, rate of energy release. Now, you see that this particular curve, which is for the rate of energy release by the reaction as a function of temperature, of course, it is like this, and the black curve is a straight line which is the rate of energy being removed as a function of temperature. Now, these two curves are intersecting at certain points. The particular thing that I have drawn here, it shows these two curves intersect at 3 points, first point here, second point here, the third point here. It may be that as you change the inlet temperature, this curve will shift, this linear curve which is the rate of energy release, it will shift maybe on this side. If it shifts on this side, or maybe it shifts on this side. So, there may not be 3 intersections, there may be no intersection, or there may be only one intersection also. So, if it goes somewhere here, then there will be only one intersection point. So, what happens at these intersection points? At each intersection you can see the rate of energy released or removed, sorry, the rate of energy removed becomes equal to the rate of energy generated, right. That is your steady state condition. If that condition is fulfilled, then the reactor temperature will not change. So, in that situation your GT will be equal to RT. So, for CSTR what happens is that if you are looking at this particular graph, this black line indicates a specific operating condition, that is being given by the specific value of T0, the specific value of Tc, so on and so forth. Now, this operating, for this particular operating condition, then you basically have 3 steady states that are possible. So, not one, you can have, so it turns out that in general you can have a maximum of 3 steady states possible for a CSTR at a particular operating condition, and you could have also one steady state that is possible for a CSTR. So, the points of intersection are the points at which the steady state lies, that is the steady state point. So, under the condition that I have drawn here, you have basically 3 steady state conditions that are realizable in this particular operating condition. Okay. So, basically this is rate of heat removal becomes equal to the rate of heat generated. So, this is something we are going to discuss in slightly more detail now, because if you want to talk about, this is called basically multiplicity of steady states. So, this is multiplicity of steady states. If you want to talk about this, you have to also talk about what we call as energy balance. We will come to that in a little while. Otherwise, we cannot talk about all these different steady states. Mass balance can only take you so far, because mass balance is actually applicable whatever, I mean mass balance is applicable in whatever condition, but the particular design equations that we derived for steady state condition considering the mass balance. So, those equations are only applicable, the final forms whatever we had derived before, they are only applicable in steady state condition, and it turns out that you can have multiple steady states for a CSTR. So, this is the CSTR dynamics that we are going to talk about in more detail now. Now, so we will do in the same way as we did for the mass balance, we will do now an energy balance for CSTR. Let us say you are considering a liquid phase reaction where A goes to B, and this is your CSTR, the drawing, the reaction mixture. This is your input Fa0, and T0 is the temperature of the inlet, temperature of the reaction mixture at the inlet. and this is what you have at outlet Fa, Fb and T. Okay. Now, so let us say you just put A and then B is also formed. So, A and B both are there because the conversion is not 100%, so on and so forth. Let H A T be the enthalpy of A per mole at temperature T. The reactor is being operated at temperature T, that is why I am putting T, steady state situation. Actually, in general we will not talk about steady state situation at the moment, we will come to that after. Just the reactor is being operated and this is the temperature here. Now, also let Q dot be the rate of heat transfer, rate of heat transfer. We talked about this, we have a jacket here. So, the rate of heat transfer, that is Q dot. Now, we can write down the energy balance as something like this: energy accumulation in the reactor is equal to energy flow in minus energy flow out plus heat transfer. I mean, heat could be transferred inside or heat could be transferred outside. I mean, heat could go inside or it could be taken away. This is your expression. Okay. Now, since this is a liquid state reaction, typically when we are talking about energy, we talk about internal energy, but we are going to replace that with enthalpy here. How? Because your H equals to U plus PV from thermodynamics, and for a, if you look at the molar volume in the liquid state, that is quite small. So, this term is approximated to 0. So, your internal energy can be replaced by enthalpy term. So, what is the rate of energy accumulation? That is ddt of, so let us say Na number of moles for A, that into HA at T, because this is per mole. So, for Na number of moles this is this, and for Nb, because for the species B this is Nb is the number of moles. So, Nb Hb T. So, as a function of time this is changing. So, this is the energy accumulation equal to energy flow in is basically Fa0 molar flow rate in into Ha at T0, because Ha at T0 is basically the enthalpy of A per mole at temperature T0. Energy flow out, two terms will be there, one term for A and one term for B plus Q dot. So, if you apply the rules for differentiation here, then what you will get? It will be Na dHa T dt plus Ha T dNa dt plus Nb dHb T dt plus Hb T Nb dNb dt, right, equals to right hand side. Now, what is dHa? Change in enthalpy is nothing but heat capacity multiplied by change in temperature. So, heat capacity is nothing but dH dt. So, dHa equals to Cpa, Cp is the heat capacity for the species A and into dt. So, that means dHa dt is nothing but, so here, so remember here this T, this small t is time, as a function of time energy accumulation here, and here it is this T, this is capital T, this is temperature. So, dHa, so rate of change of enthalpy with temperature is basically your heat capacity, right. So, if you take derivative with respect to time on both sides, then you have dHa d small t equals to Cpa dt dt. This is rate of change of temperature with time. Okay. Now, if you are considering, so this is energy balance, we are not yet done with this, we will go ahead with that, but let us stop for a while and do the mass balance. So, from mass balance dNA dt, because dNA dt the term is there, we are going to replace this. So, from mass balance this dNA dt is nothing but in flow rate in, flow in minus flow out plus RAV, we talked about this, and dNB dt flow rate in, that is 0 because nothing is going in for compound for product B plus RBV. So, if we replace these terms and this term in this particular expression, then what we get is the following. We get this NaCPA plus NbCpB dt dt capital T small t here, okay, plus HAT into Fa0 minus Fa plus RAV plus HBT into minus FB plus RBV equals to the right hand side. You can actually replace these things there and you can see for yourself that that is the expression that you will get. So, ultimately if you take this on the right side and remember that the right side is this thing, so you can work it out by yourself, it will be coming as something like this NaCPA plus NbCpB dt dt that equal to Fa0 HAT0 minus HAT into Fa0 plus RAV minus HBT into RBV plus Q dot, and remembering that RA is nothing but minus RB, okay, rate of destruction of this is the rate of formation of this. So, this minus you can put on this side and replacing there, and also you remember that enthalpy of A, molar enthalpy of A at temperature T is nothing but molar enthalpy of A at temperature T naught plus heat capacity into T minus T naught. If you remember this thing and if you replace that in this particular expression, then the finally what you get is the following NaCPA plus, it is taking a while, but ultimately it is very useful expression, you will see, I hope. This is the expression here, it will be equal to minus Fa0 CPA T minus T0 plus HBT minus HAT into RAV plus Q dot, right. Now, this particular term here will become 0 for a steady state CSTR. For a steady state CSTR, this particular term will become 0. There is no temperature change with respect to time, that becomes 0. And for a steady state batch reactor, you know this term will be 0 because there is no flow rate in. So, for a steady state batch reactor, this term will be 0. So, this is the overall energy balance expression without considering steady state. If you are considering a steady state CSTR, then this term becomes 0, and if you are considering a steady state batch reactor, then this term becomes 0. What about this term? This is basically the enthalpy of reaction. This is basically the enthalpy of reaction. And what about this value of RA? RA is basically minus K into Ca. Okay. So, actually we have run out of time today. So, what I will do is that we are very close to deducing the final expression. So, you have to just work your way through this maze of equations, but ultimately the concept is very simple. It is the rate of energy, it is the energy accumulation equals to energy flow in minus out plus Q dot. So, from there we are just manipulating the different expressions, replacing things and trying to make things easier, and you see already here the delta H reaction appears, that is the enthalpy of reaction. So, this will be negative if the reaction is exothermic. So, we will stop here today and we will continue with this in the next class. Thank you.